Hey guys, it's Mr. K here. Hope everyone's doing well. I made this video to kind of teach one of the last topics really of our calculus curriculum. It's still finding volumes, but it's using the washer method. We learned the disk method. This is going to be a kind of a step forward from that. What if the volume of the object you're creating looks a little bit weirder? What if it's not totally solid? And let's start it up. Okay, so let's look at this first problem. Find the volume if the region enclosed by y equals radical x and y equals x squared is rotated about the x-axis. First of all, it's a good idea to know which one is which. You should be able to tell without a graphing calculator. The quadratic one is probably just the one that opens up. That's x squared right here. And the one that does the other thing is the square root function, square root of x. So our goal is to take the area in between there, which, let's highlight, green. Take this area and rotate it around the x-axis, so around that way, okay? And unlike the other objects, if you actually rotate it, you'll notice that, first of all, this point will end up over here. It's going to be, you're going to have a symmetry here. This will end up down there. This will end up over here, okay? But it's not just two flat things. It's an actual three-dimensional object. So let's look at this. This random point there, this random point here, rotate around. But now if you're looking, there's another point here and here, and this will rotate to here. So that's like a gap. So you can't just use a disk because it's got a hole right in the middle. So, quick side note, if you have a disk, but it has a hole right in the middle, and you want to find the area of this is called a washer, hence the washer method. Okay, so how do you find the area of this? Well, you need to know the big radius, right? The big radius, the radius all the way to the outside, we'll call that capital R of x. And then you need to know the little radius, this little guy. We'll call that lowercase r of x. Now, if you want to find the area here, you take the area of the big circle. Big circle will be pi times big radius squared. In fact, let me just leave off the of x. Pi r squared, right? That would be the area of the entire circle. But we don't want that. We want to cut out the area inside here. I want to cut this out. So I subtract the area of the small circle, which is just pi times little r squared, little radius. That's it. Now, if this is the area of the face of this washer, we can find the volume pretty easy by just multiplying it by the thickness. And the thickness, again, will be either dy or dx, depending on if your washers are stacked up vertically or stacked up horizontally. Okay? And since we're adding them up, you know we're going to be doing an integral. But this formula for the area of a washer is what we're going to turn into the volume of this weird shape. Okay? So if you could imagine that, this rotates all the way to there, and that's open. This, I'm just going to draw a bunch of random ones, rotates to that, but there's this area inside that's open. There's an infinite number of these washers being stacked up vertically and lined up horizontally. So let's think about it. This now becomes an easy way to remember how to find the volume of a bunch of washers. It's exactly what I have written here, but I factored out the pi. And so what do I have? All I have is big radius minus the small radius, because they both have pi. And of course, times the thickness. So usually be dx, but you never know. Down here, exact same thing, except now you integrate it because you're adding up an infinite number of these. Okay, so let's actually put it into practice on this problem. First, you got to determine what's the big radius, what's the small radius. Well, if I'm looking at this disk right here, big radius would be from here to here. That's radical x. So you might want to start by doing capital R, big radius is radical x. The little radius would be from just here to here, little radius. That is, well, I guess I should do it upward so you guys can see better. That's the little radius, and that's just this function right here, which is x squared. Okay, so let's do, the hardest part is probably making this function for volume. So let's do that. Volume equals, it couldn't hurt to start with that. Well, we know it's pi, circle's involved. The integral, since we're adding all these washers up, and where am I going from? Well, if they're lined up like this, then I'm going from here to the end, which is right here. So that'd be 0 to 1. 0 to 1 of, let's see, there's a big radius minus a small radius. Well, I labeled them right here, so big radius squared, I should say. So it's radical x squared. Why is it squared? Because that's how you find the area of a circle, right here, radius squared. Minus the area of the small, which is pi, got it. A small radius, x squared, but that also has to be squared. Again, because pi r squared is the area of a circle. Okay. That setup. I'm going to be doing this video pretty fast, so it's not super long. I'm going to try to make it fast anyway. Feel free to pause at any point. Try to wrap your head around something. You want to ask me any questions, shoot me an email or message me on Canvas. Both those things work. So that's the formula. That's the setup. Now what do we do here? Well, I'm just going to simplify. Look, I have radical x squared. That's easy. That's just x. X squared squared. Well, that's just x to the fourth. So, bam. There it is. That simplifies to that. And now you probably know I'm just going to take an antiderivative. This is a nice, pretty easy thing to take an antiderivative of. Right? So, antiderivative, bam. There it is. Hopefully you can see how this easily leads to this. Kept my pi outside because I don't want to deal with it till the end. Antiderivative is in here. And then, of course, I use my notation to show that I'm about to plug in the 1 and 0. That's exactly what I'm going to do right here. Pi is still out there. Plugging in 1 is pretty easy. Plugging in 0 in this case is really easy too. You just get 0. Okay, simplify it. You get 3/10 pi. Okay, make sure you understand all those steps. That's really all the washer method is. Okay, the disk method is a little bit easier, but you got to know when to use which one. And the only way to do that is to look at the graph and figure out, wait a second, when I rotate this area around, is there going to be a space in between? Is it hollow? If the volume of the thing you're about to create is kind of hollow, then you need to use the washer method. Okay? So there's the formula. Some quick notes. The capital R is the radius to the outside of the object, and the little r, I guess it's of x, the little r of x is the radius to the inside of the object. Okay? Let's try one now where we're revolving around the y-axis. So we're revolving around this. Okay? So chances are, you could already see our washers are going to be stacked up the other way. So instead of dx being the thickness, we're probably going to have dy as the thickness. In fact, I have a PowerPoint about this. Let's take a look. And again, I'm going to be going through this kind of quick. Feel free to pause, do whatever you need to, and shoot me some questions. Here we go. Looking for the region. This thing rotates it nicely. You can see it. That's what the shape kind of looks like. And it definitely is hollow. Okay? It has a cone inside this upside down dome, I guess. On the volume. Horizontal slice. They draw it for us right there. You can tell that is a washer. Yep. Volume of the washer is the area of the face of the washer times the thickness, as always. And there it is. I would factor out a pi, Big R is your big radius, little r is your little radius, and we just got to figure out which one's which. Factor out to pi. In this case, the thickness is dy. Outer radius and inner radius. So let's look at this picture. The outer radius would be all the way to here. From here all the way to here, and that's just x squared. The inner radius is from here just to there. So that would be 2x. So we know the functions, which one's on the outside and the inside. But since they're written this way, since we're going along the y-axis, we have to have them, since we're going to have a dy, they have to be written in terms of y, which means you have to change them to x equals. Luckily, these are pretty easy functions. Y equals x squared was the outside function, and now they're just changing it to solve for x. Okay? And I know it's plus or minus, but since we're only using this part for now, that's going to be our major side. They just use the positive version. Other one is 2x. This is the inside. And they solve for x, so that's just y over 2, or 1/2 y. Cool. There it is, the volume using that formula. Oops. Let's see. This is the capital R squared. This is the little r squared. Usually pi I pull out immediately, but you know it doesn't matter. It is a constant. Now they're simplifying. Radical y squared is just y. Y over 2 squared, you square the top and bottom. Cool. Then you can take an natural derivative. Pull the pi out. Well, they pulled the pi out in a whole step. Then they did the antiderivative. Yeah, buddy. The y becomes 1/2 y squared. The 1/4 y squared becomes 1/12 y to the third. Again, pause that and check if you're not sure. And now we're going to plug in 4 and plug in 0, which in this case will be 0. Plugging in 4 gets you that. And simplifying gets you 8 pi over 3. Okay? So what makes this one tougher is that they were written in terms of y, they were written as y equals, but they were stacked this way. The washers were horizontal. So we need to use dy, so that means you need to solve for x in each one and make it in terms of y. Like this and like that. There's these notes, the exact same formula that we already showed. Now the next one in your notes is this one. It's the exact same area with the exact same curves, but this time we're going to rotate it around the line x equals 2. So things are going to be a little bit tougher. There's the line x equals 2. We're going to rotate it that way. So the shape is different. Now it's like a cone on the outside, and the inside that's hollow is more curved. Okay, but you can see to find the volume, we still have to stack up a bunch of washers because there's a hollow space inside. Our job is still to find the outer radius squared minus the inner radius squared. This is a little bit tougher because things are moved off the axis. So let's see. The outer radius. Outer radius would be from here to here, that whole thing. How do you find it? Well, you take 2, because that's where it starts, and then subtract the value here. So it's 2 minus that function. Okay? Make sure you see the picture and understand it is 2 minus wherever the function is. So that one clearly is now a little bit different. The inner radius, labeled right here. The inner radius is from the 2 just to here, wherever this function is. So it's 2 minus this one, which is radical y. So once you have the outer and inner, again, now you use the formula, which is that. And we are going 0 to 4. Remember, these are dy's. So we want to go. Declan, you got to turn that way down, buddy. Like, keep going. Keep going. Good, that's good. Sorry about that, guys. That's my son. All right. Where was I? The dy's. Lost my track. Oh, yeah. So we want to make sure the interval of integration is this way along the y-axis from 0 to 4. So that's where they're using 0 to 4. Big radius we have. Little radius we have. We put them in there and square them both. And you could already tell this is going to be kind of a pain because we have binomials squared. And so we're going to have to expand them, combine like terms, before we start trying to find the antiderivative. So there's the expansion. Basic binomial expansion there, multiplying this, each binomial by itself, and using FOIL, or double distributive property. Looking for like terms. They distributed this minus sign to everything to get rid of parentheses. Now they see, okay, got some things to cancel out there. Few like terms. And now at least we have one solid polynomial. We can take the antiderivative, which is right there. And, of course, they're going to plug in 4 and 0. Don't forget the pi. Okay, it's easy when you go through all this stuff that at one step, you forget the pi and it's not a big deal. But then if you forget to bring it in at the end, it's a really big deal. So just get in the habit of writing pi in every step. Okay, so you don't forget at the end. There, they're plugging in 4. Plugging in 0, again, would get you 0, so they're not even going to do it. When you simplify that, you get 8 pi over 3. Yeah, that was a wicked one. Okay, that one's crazy. But be ready. Go ahead, buddy. Okay, good. We did that. All right, this is the last one we're probably going to do. I'm not sure how long this video is yet, but I'm sure it's not short. All right, let's take this and rotate it about the line y equals 1. So this is the exact same thing as the first one, except instead of rotating around an axis, let's practice rotating around a line that's not an axis, like we just did. This is the region. Here's x squared. Here's radical x. The line y equals 1. Here's y equals 1 right here. So now if we rotate this, and actually rotate kind of upward, this is going to end up like that. It's going to end up like that. Okay. This is going to rotate around a random. Just look at a random cross-section here. This point lines up with this. This point lines up with that. This will rotate around to there. But look at the middle. This will rotate around to there. So therefore, our three-dimensional shape is going to be hollow. It's got a area inside, which means instead of discs, we have to use washers. Okay, we're ready for this. Let's find, first, probably best to find big R. And then find little r. What's the outside radius? What's the inside radius? Let's see. Use green. From the axis of revolution, the outside radius would be from here to here. How do I find that? Well, if I use the function, it would be this whole line. But I don't want this whole line. I want to take out 1. I want to basically take out this. I only want that. So it would be, oops, you know what? We're going to go back. Instead of using the rotation image, let me use the original image right here. Let me use this curve and this curve. Sorry. So I'm going from the middle out to here, the big radius. So what I'm doing is I'm taking 1, which is the whole thing. I'm subtracting out the value of the function, which is here. That'll give me the solid green line. So what I actually have is 1 minus the function here, which is x squared. Okay. To find the little radius. That'd be from here to here. Do the same thing. Take 1, which is that whole thing, and just subtract out the value of the function, which will subtract out all this, and I'll get left with the inner radius. So it gets 1 minus radical x. Okay? I know that's a little bit tough, especially when you got to hand draw the function. If they have you using washer method on an AP test, usually it will be an image where both graphs are clearly laid out in front of you in some picture. So it should be easier, hopefully, to find out what leads to the bigger radius, what leads to the smaller radius. Because once you do, you just got to use that same formula that was right up here. So let's do it. Volume equals pi. This time, let's see where we're going from. We're going from, the discs are stacked up from here to here. We're going to be using, the thickness is dx, so we'll be using the x-axis from here to here. 0 to 1. Of, let's see, the big radius squared. 1 minus x squared squared. Minus the little radius squared. 1 minus radical x squared dx. Okay? Now, again, you see that this is going to require expanding this function, and doing the antiderivative. And this is for the sake of time. I plugged it into calculated forward. This is not going to turn around, so just turn your head and look at the screen. I typed it in very carefully. I double-checked that what I typed in was right, and then I got that. I thought, you know what, that's a decimal. I want pi in my answer. Notice I did not put pi up here. I could have. It would have just given me a different decimal, but I want to try to get a fraction with pi. Again, not that it matters, because equivalent forms are equivalent. So as long as you round to 3 decimals, you're cool. I got this answer. I said, all right, let me change that into a fraction. But it wouldn't. It gave me the same thing. So I said, well, maybe it's just rounded too small or too soon. So I rewrote it like this, 0.3666, and I wrote a lot of sixes, and then I changed to a fraction. Then it actually did for me, 11 over 30. Now I'm not going to forget, go back so you can see all my stuff on that screen. There it all is. That's how I did it. That's how I got the fraction. So I got 11 over 30 pi. That is the volume of this figure. Okay? Again, feel free to look back, look at the video, go slow, go fast, whatever you need, but I will be available for questions. I'm going to put up a practice as well. Look up the 8.3 homework washer practice, what it'll be called. It'll be like 4 problems. And then after that, tomorrow, I'll probably put in a mixed volume practice where it'll be discs and washers, and it'll be mixed, and you kind of need to figure out which one is which. This one we're not going to do. We'll do when we come back if there's time. It's the exact same question as number 2. Exact same question as the one before it. But it says that, let me give you a quick preview, instead of doing it like this, you can actually, if the line of axis is here, axis of rotation is here, you could pretend that you move everything down. So you can move this to the x-axis, but then everything else needs to move down as well. So in red, the new axis of rotation will be here. The new function would actually be here. And the rotation would end up here. Okay? Basically what you would do is you're taking the original functions and just turning them into radical x minus 1 instead, and x squared minus 1 instead, just so that your axis of revolution is actually on the x-axis. Okay? It's just another way to do the exact same problem we did. It's not easier or more difficult. It's just another way. You'll see that. See? These things right there, rewriting them, it's going to get you something that looks like the opposite of what we did here. And you might think, wait, but they're the opposite. They're not the same. Well, we're squaring them. So even if you put in the opposite and you got a negative, when you squared it, it didn't matter. It's going to be all positive anyway, and you will get the exact same answer. It's just another way to do that. I can show you how to do that when we come back. Okay? Okay, hopefully in 2 weeks, but we'll see. Again, that's the end of the video. If there's any questions, please shoot me a message, an email, whatever. I'll try to be on all day today, and I'll just keep posting announcements to let you know what I expect of you. Don't forget the test is still going to be Thursday, so make sure you're looking at the review packet. The review packet has no volume on there. It's everything else. It's area, it's that particle stuff, it's displacement, total distance, things like that. And then I'll post another review, which is going to be like the mixed volume review, discs and washers. All right. Thanks, guys.